Now let's try looking at the Paris Handbook for the thermodynamic properties of oxygen. Now in this case, what you have here is table 2-245, and as you can see, there are a lot of properties here from the temperature up to the viscosity. Now the viscosity here is expressed in micropascal second, that is a dynamic viscosity. There's also the specific heat capacities here, the Cv and Cp. Now we'll be using Cp since we're assuming that there's a constant pressure in the system. Well, the constant volume is different since there's no constant volume but a continuum. What we need to do here is to find the properties that must be used in evaluating the Reynolds number. That is the density and the viscosity. So with that, let's take some kind of rectangle, and I will shade that portion where will we be interpolating. In our problem solving, what we have here is the temperature of the film temperature, which is 350.15. That is the average of the surface and the free stream. Now in this case, since this is 350.15, we need to look at the temperature here, where there is 350.15 and 2 atmospheres. But as we browse over this Paris Handbook, what you can see here is just temperatures ranging from 54 to 154. You can also check on other values and then single phase properties, but what you will be getting are also temperatures from 54 to 154 and this. Now this is very essential since what you can see here is the temperature in a different single phase properties, which is at 0.1 megapascals and then 1 megapascal. If the problem says that there's 2 atmosphere, if we convert that to megapascals, what you will be getting is 0.101325 times 2, so that's around 0.20. Now in that case, since we don't have any value for our 0.20 megapascal, what we need is to interpolate in between this 0.1 and 1. Now the idea here is to do some kind of double interpolation. If you haven't heard of double interpolation, the first one is that we are interpolating between the values of a fixed pressure, where we'll be using the temperature or the film temperature here. So we'll be able to find the values at the film temperature at 0.1 megapascals. We'll be doing 0.1 megapascal. We'll be doing the same thing for this section here where there is a higher pressure. That is, we'll be interpolating at 1 megapascal where the temperature is the film, which is 350.15. In that case, you'll be getting a set of values from 1 megapascal for the density and the viscosity. With that, after interpolating, so since this is what we call the double interpolation, after interpolating, we'll be interpolating again in a way that we'll be considering the difference in pressure, since we'll be interpolating 0.1 and 1 in between the 0.2035. So upon interpolation, what will we be getting are these values. So I won't be showing you how to double interpolate since should have known that. But if you're not familiar with how this interpolation works, this is how we do it. The first one is that we interpolate. As what I've mentioned before, you need to interpolate in these values here from 300 to 500 and interpolate at 350.15. So of course the pressure will just be 0.1 megapascal, same as this given, and then you'll be getting the densities and then the viscosities. So these are the values that I have already pre-interpolated. And then after that, you also interpolate at 350.15 in this section. So you have already, and then you will be interpolating between these values using the pressure that we need, which is at 2 atmosphere, which is around 101.10135 times 2. So after that, you'll be getting the densities in between these values, and the values there would be the thing that we need in order to solve for the Reynolds number for this problem. Now, since I've already given you the values that I've interpolated, you might also want to pause the video and try to interpolate in between these properties. You can't actually see the viscosities and thermal conductivity on the screen, since there is some kind of, I think I can, I don't know. So probably we can just zoom in, and yes, zoom in again. So there you have it. The last portion here would be the values for, I think it's thermal conductivity, and yeah, viscosity, sorry. So this will be the viscosities, and this one will be the thermal conductivity. So you just have to interpolate there, and you'll be able to get these answers. Well, these answers are the same unit as these data here. And after that, you need to convert them into the MKS unit SI, so it'll be easier for us to solve it. So after that, what we'll be getting are the values of our film. So the values of our, so we need the density at the film. So the density at the film temperature is equal to 2.3459 kilograms per cubic meter. And then the viscosity, or the absolute or dynamic viscosity at the film would be 2.3139 times 10 to the negative 5 Pascal second. So the unit is very important. You have to consider the MKS unit for SI. Now, since we already have this density at the film and then the viscosity at the film, we can now solve for the Reynolds number along the X region. So in this case, I'll just be substituting the value. So X, in this case, X will be 50 centimeter, and 50 centimeter, this is equal to 0.5 meters, 0.5 meter. So we have 0.5 meter, and then we multiply it with the density, which is 2.3459, then that's kilogram per cubic meter, and then multiply it with the velocity, which is 30 meter per second. That is the velocity of the fluid. Now, since we already discussed about this boundary layer and then this velocity that varies along the, from the boundary to the center line, the velocity that we're talking about here is the free stream velocity, that is the average velocity at the maximum one. So we divide this by the dynamic viscosity. So that's negative 5 and Pascal second. So we cancel all these units since this one's dimensionless. So what we get here will be the Reynolds number, and the answer here will determine what kind of flow region will we have. So we get 1.5208 times 10 to the 6, and this one is turbulent. So in this case, the flow region of our oxygen across our plate is across a flat plate isothermal, which is a forced convection, is turbulent. So with that condition, or with those conditions, we can now proceed with number 2, which is select the appropriate equation. So in that case, let's check on the Paris Handbook and let's find the appropriate equation we'll be needing here. So I think we'll be going back to this table after we've already determined the correct equation that we'll be using. So we go on heat and mass transfer, and then proceed to heat transfer by convection, and then this one, the forced convection. So there's a lot of wordings here, and what we need here is the equation for, so this one is the one that we need. Okay, so I think I'll be zooming, and then I'll just be taking a snapshot of this, and we'll be using this as our let's have, okay, so we'll be using this as our working equation. Let's try to maximize this space. Okay, so in this case, since, let me just equate this to H and then X, and then we'll be needing this H here. Okay, so in this case, if we want H, then we just find the value here and then multiply it with L and then divide it by X. Now let's analyze all the necessary properties that we need here. The Prandtl number would mean that it's the Prandtl number at the film temperature. So we need the Prandtl number at the film temperature, also the Reynolds number at the film temperature, which is already obtained. Let's do some REX and then the film. So it's already done. And then the one here that is the critical Reynolds number is already given in the Paris Handbook. So it has a numerical value here. So it says here that the critical Reynolds number is typically taken as 5 times 10 to the 5th. The screen actually cuts it off, but let me just zoom in. So yeah, as you can see there, it's 5 times 10 to the 5th. So we'll be using that. And for further reading, you can see that the fluid properties are evaluated at the film temperature. So this is what I'm doing before. So anyway, so the Reynolds critical number would be 5 times 10 to the 5th. So we'll be substituting this value to the critical Reynolds number. And then I think that's all for now. We need to find the Prandtl number at the film temperature. So remember, the Prandtl number is actually equal to the specific heat capacity and then the viscosity divided by the thermal conductivity. So of course, all of these will be evaluated at the film temperature. Since we've already obtained the Reynolds number, we needed to obtain the value for our viscosity, and with that, we're already we don't have to find the value of our viscosity the dynamic viscosity at the film temperature, since we already obtained it. Now we're only left with the specific heat capacity and the thermal conductivity. So with that, we need to find Cp of F and then K of F. And then remember, we did some double interpolations. So these double interpolations, will be using that to find Cp, F, and Kf. So we're going back to the table that we use. So that's table 2 the thermodynamic properties of oxygen. So it's around 320, I think. So octane, this one. So this one's the oxygen. So again, we'll be interpolating in between these values, and as you can see here, I've already pre-interpolated all the values that we need. So you have there the Cp and then the K. So after doing some double interpolation, you'll be getting this specific heat capacity for each temperature and pressure. And then after that, you'll be interpolating in between these two. So I hope I hope you can follow through that double interpolation. So if not, then you can tell me. I will show you how. But knowing that you already know how to interpolate at just these two values, I think you already know how to do some double interpolation. So again, I wanted to repeat that you just have to interpolate in between these using 350.15, jot down all the data that you will get, interpolate here in temperature 350.15, but that's our film temperature, and then jot down all the data, and then interpolate again in between 0.1 and 1 megapascal where the pressure would be that 2 atm. So this would have been easier if the temperature is around 1 atm or 0.1 megapascal. In that way, we'll just be using these the values here, and we're done. Or in 1 megapascal if the pressure is 1 megapascal. But since it's not, then we need to do some interpolation just to make the data accurate. So with that, upon interpolation, I will be able to get a value of the specific heat capacity at the film temperature, which is 934.2783, and then the unit here will be joule per kilogram Kelvin. So in Paris Handbook, what you have there is a unit something like joule per mole Kelvin. So what you have to do there is to multiply it to joule per kilomole Kelvin. So with that, you have to multiply your answer to something like it's kilojoule per mole Kelvin. So what you have to do there is to multiply this, convert this kilojoule into joule, and then this mole to kilomole, so that you will be getting kilogram upon multiplication to its after dividing it to its molecular weight. So in this case, so I performed that, and then I obtained this specific heat capacity. Yeah, I mean, it's just dimensional analysis, so you can do it anyway. So I need to find the thermal conductivity at the film temperature. So with that, we have 0.0270 watts per meter Kelvin. So if I have some time, I'll be adding some video how I do double interpolation in this. I mean, probably after the solving process, just to make sure that you know how to do it. But I still believe that you already know how to do that. So with that, now let's try finding the value of our Prandtl number at the film temperature. So our Prandtl number at the film temperature is Cp mu over K. So we get 934.723 multiplied with our dynamic viscosity, that is, we already obtained it, so 2.3139 times 10 to the negative 5. When we divide this by the thermal conductivity, that is 0.0270. So what we'll be getting is our Prandtl number at the film temperature. So we have 0.8007. So knowing all of these values, we already have the things that we need, so we can now proceed with substitution to our working equation. But before that, let's just head over this portion here at the Paris Handbook, which is just below the equation. It says here that this equation is only applicable when the critical Reynolds number is greater than, the Reynolds number that you have obtained for the problem is greater than the critical but less than 3 times 10 to the 7. So ours actually falls in that standard or case, since ours is less than 3 times 10 to the 7 but greater than our critical, which is 5 times 10 to the 5th. And the second condition that we need is that it says here that the Prandtl number should be 0.7, greater than 0.7 and less than 400. So in that case, we have 0.8, so it is applicable. So what if you've already obtained all these values and then it doesn't fall or doesn't fit to any of the satisfying conditions that we need? So what you'll be doing is, probably the problem would state that you'll be using a certain kind of equation, and with that, that's the thing that you'll be using. But in case-to-case basis, when there is no hope left, I think, and you don't have some kind of references that you can use. By the way, I'm not allowing you to use some kind of equation from other books, simply because you're only allowed to use Paris Handbook at your board exam. It's like we're practicing at your board exam. So in this case, you have to familiarize yourself using these kind of equations that are presented in your handbook, because I don't think you will have an ample time memorizing all of those equations presented, knowing that they're very long and they're not really easy to memorize. But if you have time, then so be it. Anyway, so what I've mentioned before, in such cases when there's no hope left, sometimes you're still forced to use this kind of equation, even if, for example, the flow is like laminar. There's another form for laminar, but of course, for example, the Prandtl number is like 0.6, so you should not be using this since it says here that it should be 0.7 and greater. But of course, when you already know that thing when you're faced with a lot of difficulty and you're trying to force out some equation. But in my case, I won't be giving something like those that won't fit the standard. It's either you have already solved some kind of problem that is not, you already obtained physical properties that are not correct, probably. That's why you can't use any of this equation, if that's in my case. Well, anyway, so let's proceed with the substitution. So the nozzle, or the average nozzle along the streamline, would be equal to 0.664. So let me just rewrite this in the critical. So there I've already written the value, the equation in which we have substituted all the values. And take note, this 625 over 1901 is actually the ratio of the critical to the one that we've obtained from the problem, and it's just the simplified form since it can be simplified. So with that, the answer for that would be, so the Nusselt number, the average, would be equal to 2137.3376, where this is equal to hx over k, where h is what we need, and then x is the dimension of the square plate, the one dimension, and then k here is thermal conductivity, which is 0.0270. So with that, the value of our h, or the convective heat transfer coefficient for the oxygen past this square plate, would be 115.4162, and the unit will be watts per meter squared Kelvin. So it doesn't end with that. We already have the h. Then we can now substitute that to our general equation that I used to tell you, that there's just one equation for either the force and the natural. So that's A, H, and then Ts minus Te. So Q, so the area is actually the area that is in contact with the fluid. So that's simply 0.5 meters. That is, you square that since that's a square. And then we multiply this with our H, that is 115.4162. So let's just write the unit. And then we have Ts minus Te. So remember, Ts is actually the temperature at the wall. So that is 127 degrees Celsius, and then the air would be 27 degrees Celsius. So evaluating that would lead us to an answer that is 2885.4050 watts. So that's all for our answer for Q. So the heat transfer that is experienced by this case for oxygen and that flows across a square plate would be 2885 watts, and that's of course convection. Now I wanted to go back with this density here. So you might be wondering why I didn't use the ideal gas equation where we have density is equal to Pm over RT. So since this is gas, we can already use that since we have pressure and then the temperature. Molecular weight would just be the oxygen, and then R would just be the universal gas law constant. So the thing is, you can actually use that, and the discrepancy I think wouldn't be much. But since I'm using all the data obtained from the Paris Handbook, might as well want to use the data that is also included in that particular book for the density. It's just some what do you call this? It's just being consistent with all that we do. I mean, since we're all taking the data from Paris Handbook, then since density is also given, so I'll be taking that data from that handbook as well. But you can also use this as a shortcut if you're finding, you have some time issues and then you need to be fast. So you can also check on the density using this Pm over RT. But I would also like to emphasize that ideal gas law holds true to at a certain temperature and pressure only. So as we increase or probably decrease a lot of temperature and pressure, it won't be that, the line in which the ideal gas is actually will be deviating from its ideality, and then it will be real gas. And with that, we need to add some factors and this and that. That's why you're not able to apply this ideal gas law, at all times. But the thing is, well, that's a good thing that real gas law would just deviate from some kind of around some percentage. But anyway, so it's just a suggestion if you're finding it difficult to evaluate the density. And of course, with that being changing, the Reynolds number will be changing, and of course the values here will be changing as well. So I don't know how much it will change, but definitely it will. I think for as long as the values here are 5 plus minus 5% deviated from this, I think that's still a correct answer. So what I'll be doing here is I'll be checking your answers, and then add some like plus minus 1 2 3%. I don't know if whichever is applicable. And then with that, if your answer is not exactly like this but it's close enough, then I'll be, of course, making it correct. But if it's clear, like if it's really deviated like around 10%, that's all. And even if it is not, and then you just use, let's say for example, the free stream temperature instead of using the film temperature, then that will be marked wrong immediately, since you should always understand that since the fluid is in contact with this plate, it should have some kind of heat exchange, and you should also consider the temperature that is in between that, not just the fluid temperature, or not simply the temperature of the solid. So with that ends the first problem. So let's move on with the second one. So the second one, I want you to read it and understand it, and let's do the things that we need to do here, just the 3 steps. Let me copy it. So we'll always be reminded by the 3 general steps that we use in order to like solve any kind of convection problems. And as what I've been telling you, the thing that is most difficult here is to determine determine the value of heat transfer coefficient. The convective heat transfer coefficient. So I hope you've already read the problem, and before anything else, let us determine the condition. So you might as well want to illustrate what happens. So I'll be illustrating that in a way that it can be easily understood. So imagine this is the side of the house. Okay. And then air flows parallel to the side of the house. So air flows through that. So we have air here. And then the direction is actually not specified, but just to show you that this is how it goes for that. And then it says here that the house is actually 3 meters by 4 meters. So at the side where it is 4 meters, that's where heat flows parallel. So we have here 3 meters. So in this case, we'll be considering the flow that is parallel to the wall. And in that case, that the length will be 4 meters. So since this is around the temperature here is of the wall is our TS, that is actually equal to 20 degrees Celsius, and we do have a very cold air. We have the stream temperature that is negative 20 degrees Celsius, and the speed is 12 kilometers per hour. By the way, this is a very cold air. And then I think that's all. The area would be something like 4 meters by 3 meters, which makes it 12 meters squared. So that's it for our given, and then the geometry is something like this. So if you would be if you need to find or determine the geometry, that would act like a flat plate, and since the temperature here is not changed, it's not specified in the problem, then we can say that this one is isothermal. and then we need to find the region of flow. So we'll be using the Reynolds number again, and in this case we have some x since it's what we need to find the Reynolds number of the air. So we have x, and then the density of the air at the film temperature, and then the velocity divided by dynamic viscosity at the film temperature. So to be able to find the Reynolds number, we need to find our density at the film and then the viscosity at the film. So again, since we can already find the density at the film using some kind of density PM or RT, but since we don't have any, so I'll be just using the the Paris Handbook. Now remember, in our previous problem, as you can see, there's this pressure that is given, but in this case we're not given by the pressure, and we need actually the pressure so that we can eliminate some degrees of freedom there and then find the thing that we need. But since it's not given, there could be probably two assumptions that we have. The air is saturated, or P is equal to 1 atmosphere, that is the atmospheric temperature. So these are just the two cases: saturated air, and then the pressure is at 1 atm. So before anything else, before we proceed with finding the values, let's just first find the film temperature, that is just the average of these two values. So we have 0 degrees Celsius, that is 273.15 Kelvin. So we need to find the temperature of the air at 273.15. So if it is saturated, then we should be able to find this temperature, this film, 273.15, at the table of values in our Paris Handbook. But if it is not, then most probably the air is not saturated, and the pressure is around just 1 atmosphere, or the normal temperature. The normal pressure. So we need to check on the table number 2 and then proceed with thermodynamic properties of air. Now here's the table of thermodynamic properties of air, and let's look into it. So here we have the temperature from the viscosity, and as what I've mentioned before, we would always assume first that the fluid is at its saturated state. Now in this case, since we're given by the temperature at the film, which is upon computing, it results to 273.15 Kelvin. We need to look at the temperature, and if we can see something like 273.15 here, then that's probably at the saturated state. Now if we look closely here, this is liquid air, and this one is, well, you don't seem to have something like liquid air, but if you would try to liquefy it, most probably that would be like nitrogen, and this density would tell us that this is actually in liquid state. And then this one's the vapor, or the gaseous phase that we always we don't see but we feel. And then the second page, you will see here, is also the saturated state at a single phase property, wherein we have something like gaseous, or the vapor phase of this air. Now in this case, since you could see that we don't have any saturated property, because this is the saturated property that we have, and in that case, since the saturated property ends somewhere at around 132 Kelvin, that is 3.7 megapascals, so we need to assume that this is at a 1 atm pressure. So that's what we do when we're considering fluids that are, the pressure system is not given and the temperature is not within the saturated properties. So in this case, we will assume that the pressure or the total pressure would be 101,325 pascals, or that is 0.101325 megapascals. But in our phases here, what we can see there is just zero point 0.1 and 1. Well, we can actually use the zero point 0.1 megapascal since it is very close, but I want to be as accurate as possible, so we still need to double interpolate from these values and then try to give as much as accurate as possible. So I'll be using 0.101325 instead of just 0.1. If you'll be using 0.1, then these are just the values, and it's very confusing right here since I actually like place it right there, but let's try to place it right here so that you can see it. So I've already interpolated all of these, and these are the values I obtained from density, viscosity, heat capacity, and thermal conductivity. You might also want to do it, and then since I'll be doing some double interpolation, I also need to interpolate again on another pressure and then take the interpolate again through these values using 0.1 megapascal and 1, wherein the pressure would be 0.101325. So using these values that I've obtained, and you might also want to interpolate as well. So with that, we'll be needing this density and viscosity at first, and to answer that, the value of our viscosity or the density of the fluid will be equal to 1.4976 kilograms per cubic meter. By the way, I used something like the molecular weight is 79% nitrogen and 21% oxygen. So this gives me the molecular weight, which is 28.84. And then, of course, I need to find the dynamic viscosity at the fluid temperature. So in this case, I use this 0.1 and 1, then interpolated 0.11325 using these two values, and of course, I'll be getting a value that is close to 17.0025. So the answer is 1.7003 times 10 to the negative 5, that is Pascal second, since this one's given in micropascal second. Now I can find the Reynolds number along the element of concern, which is our x, and then we get x density FV divided by the viscosity. So x here could be 3 or 4, but since the air flows parallel to the side, which is 4 meters, so we'll be considering 4m instead of 3. So we have here 4 meters, and then the density would be 1.4976, that's kilogram per cubic meter. And then we also have the velocity, and the velocity here is in kilometers per hour, that is 12. We'll be converting this 12 kilometers per hour into meters per second, so I'll be having something like 1000 here, and then 1 hour is 3600 seconds. So divided by the viscosity, which is 1.7003 times 10 to the negative 5 Pascal second. So with this, the Reynolds number is equal to 1174380.992. So that's around 1 to the 6. 1.17 to the 6th. So this is turbulent. So therefore, the condition, we could say that it is a flat plate and it's isothermal, and then the region is turbulent. So it's the same as the previous one. So with that, we'll be using the same equation that we used before. So we'll be using this again. And when we use this kind of equation, we also have to find the values that we need to solve before. So we need to find the Prandtl number and, of course, evaluate that at the film temperature. So in evaluating this Prandtl number, we need to find the Prandtl number at the film temperature that is equal to the Cp, viscosity, and then thermal conductivity at the film temperature. So we need to find Cp at F and then the thermal conductivity at F. So if already found that, then we can substitute all the values. Now, let's go back. I have already pre-interpolated all the values here. So here I've got the heat capacities and then the thermal conductivities. So they're quite close to each other, and let's just substitute all the values after interpolating at in between 0.1 and 1, which is at 0.111325. So in this case, I have specific heat capacity that is equal to 1015.3786, and the unit will be joule per kilogram Kelvin. And then the thermal conductivity is equal to 0.0241 watts per meter Kelvin. And as you can notice, the thermal conductivity of our gases are almost like the same, around 0.02 to 5 to 7 to 4. So the values of our thermal conductivity should lie along those values. And if you've gotten something like 100 for thermal conductivity, then you might need to review your answer since we're considering gases there. So gases don't actually conduct much of the heat, but but metals do. So anyway, let's just substitute the values here. Remember the Reynolds critical number, or RECR, that is equal to 5 times 10 to the 5th. So we need to substitute all those values, and probably you'll be able to get. But before that, let's just find the Prandtl number. So we have 1015.3786, and then multiply this with our viscosity, which is 1.7003 times 10 to the negative 5, and then divide this all by the thermal conductivity, which is 0.0241, and what we will be getting here is 0.7160. Remember the condition in which the Prandtl number should be greater than 0.7, so we still satisfy the condition, and our Reynolds number is still less than the 3 times 10 to the 7, so we still can use this kind of equation. So we'll be substituting all of these values. So we have the nozzle, average nozzle along the x path, so that is equal to 0.664, and then the Reynolds critical, we have 5 times 10 to the 5th raised to 1/2, and the Prandtl is 0.7160, and then raise that to 1/3, and then add some the rest of the equation, and we'll be using here our Reynolds number that we have obtained. So we obtained 1,174,380.992, and then that's raised to 0.8, and then the Prandtl number, which is again 0.7160, that's raised to 0.43, and then we have 1 minus, so I just pre-calculated this ratio, so I have 0.4258, and then that's raised to 0.8, then close bracket. So what we'll have here for the Nusselt number average along the x path would be is equal to 1527.5034, and that is a dimensionless number. So this Nusselt number, that is equal to h and then x divided by k, and we have the value of x, that is 4 meters, and then k being the thermal conductivity, which is 0.0241. So finding the value of h, we just need to like cross multiply, and then the answer would be 9.2032, and the unit would be watt per meter squared Kelvin. So we already have the value of our h. Now we can substitute that to our equation to find our heat. So that is QAH, and that is Ts minus Te. Substitution for that, we get 4 meters, and then multiplied with 3 meters since this is the area, and then we have H, so that's 9.2032. That's the convective heat transfer coefficient we've obtained from the Nusselt number, and then subtract this with our surface temperature, that is 20 degrees Celsius at the plate and then or the wall, and then negative 20 for our air, so that becomes positive. So what we'll be getting here is 4,417.5398 watts. So this is the answer for this problem. So the air that flows parallel to this wall would be conducting a heat that is 4,000 watts, or that's 4 kilowatts in estimates. So I hope you've understood how this lesson works, and let's proceed with the last number.